Hello and welcome to Adventures in Algebra. Today we're going to be talking about a new chapter, which means we're going to start talking about a new mathematical object. Specifically, we are going to be learning about exponential functions. Now the name of this comes from the idea of an exponent, and we've talked a lot about exponents previously in this class. So far, we have seen things like b to the n, where we would have b as the base, and n would be the exponent. That doesn't look like a word. That happens a lot. Okay. Oh, that's fun. So we've seen things like, x to the fourth when we've been doing polynomials, where here x was the base and 4 was the exponent. So with this kind of example, our variable was in the base. But we've also done things like, 4 squared, where we've had both of the values be numbers or constants. So 4 is the base and 2 is the exponent. Well, exponential functions are going to put the variable in the exponent, hence the name. So it's going to be things like 4 to the x, where x, the variable, is, I've been putting base first, so we're going to stay consistent, and I'm going to put the base first. 4 is the base, and the exponent, x, is going to be the variable. So let's take a look at calculating some exponents where x, the exponent, is a little bit different from what we've seen so far. So for this example, we're going to approximate each value with a calculator. So I'm specifically writing things to the side so I can fit a calculator over here on the other side. Let's go ahead and scroll this up. So first up, I'm going to do 2 to the 1.2, and then I'm going to do 4 to the square root of 2, or n because I wrote the wrong thing. And we're going to get what this is using a calculator. So we're going to have to do some rounding. So instead of writing equals, I'm going to be using the approximate squiggly, so close to this. So let me pull up my calculator. Now I'm using the Windows calculator, and I'm specifically using the scientific side of it. If you use the standard calculator, it actually doesn't give you the ability to do any exponent other than squaring. So you might need to change your settings if you're using a computer to switch this over to the scientific one. Okay. Now on your calculator at home, it might be a different button, but I'm going to be using the x to the y button. So to use this, you have to put in your base first, and then you hit the x to the y button and put in your exponent, 1.2. So there is my answer, and I think I'm going to round it to just 2 decimal places, so 2.10. Now, if your calculator doesn't have an x to the y button, you might have to use a different button to get your exponent. So a lot of calculators use a caret key, and it looks like a little up arrow. So you would write it in your calculator as 2 up arrow 1.2, and that tells it that this 1.2 is all in the exponent. So if you've got something more complicated in the exponent than just the 1.2, you might need to use parentheses on it, just so you know, and that will come out just like mine, 2.10. So for instance, in this next example, if you have to use the caret key on your calculator, you would type it as 4 caret parentheses, use your square root button, put in the 2, and then close it. Now, my calculator, the Windows one that I'm using, doesn't have the option to do parentheses, I don't think. I had to look again to be sure. It does, so I should be able to get away with this. So let's clear, and we'll put in 4, and then our xy, and then we'll do a parenthesis so it knows I'm going to do something extra. Where's my square root key? I always have a hard time finding it on this one. I don't see it. I don't think I have a square root key. Uh-oh. Yeah, I don't. What am I going to do? Well, hopefully you remember, square roots are the same as fractional exponents, so I'm going to use an exponent again. So I'm going to put in 2, another caret, a second parenthesis, to the 1/2 power, because that's the same as a square root, close my first set of parentheses. So notice I've got that 1/2 in the exponent there, and then close it again, and there is my answer. And that is not the correct answer. That didn't work. I don't think I can use this calculator to do this, because you should get 7.10 and some change, and it's coming out 1.4. Let's try this a different way. Let's try again. Clear, clear, clear. So let's try doing the square root of 2 first. So we're going to 2 caret 1/2, and that should be like 1.7 something. Oh, did I have a typo? That looks wrong. Okay, let's try this again. 2 caret 1/2, 1.14. Okay, that is the correct square root of 2. And then what I want to do is I want to do 4 caret, and then steal the last answer I had, this value, and put that as my thing I'm going to do as the power. Copy. Double click this. There's no answer key on this, so I can't like store and recall. Can I paste? I can. There we go. Copy and paste it. Bam. That's the correct answer. I don't know why that didn't work the first time. I don't really like the Windows calculator. If you have the standard TI-30X, which is the blue one, or similar, any of the TI-30 series, you can just, use the answer key to do this. Or if you need help with that, please don't be afraid to ask, but you should get 7.10. Let's do let's do 2 more. C. We'll do e to the 1.1. Now if you remember e is just a number between 2 and 3. So to do this, we're going to use the e key up here. So we're going to clear this off and do e, so that's my base, caret 1.1 equals, and you get something just a little bit bigger than 3, but we're going to round it to 2 decimal places and call it 3.00. I don't know why I picked 2 decimal places. I really should have picked bigger so that it would have a... Oh, no, I want my whiteboard, thank you. No, okay, good times. Oh, why is it doing that? There we go, black pen. And then let's do D, let's do e to the negative 0.25, negative quarter. See what happens there. Pull up our calculator, clear it off again, e, caret 0.25, and then make it negative because the Windows calculator is weird, and hit equal sign. Ooh, 0.78. Had to round it. Just make sure you can see that calculator one last time so you can see my rounding there. Now, one thing to notice about this is hopefully you've seen that all of the outputs I've had here, regardless of the base I used, have come out positive. Also, regardless of the exponent I chose, it's come out positive. This is a characteristic of the exponential as a function. Let's talk about that. So, an exponential function f of x with base b. We've got some requirements on this base, but I'll get to that in a second. Is of the form, so it looks like, that's what of the form means, f of x equals b to the x, or if you don't like the f of x, you can use y, b to the x. Yeah? And then we've got some requirements on b. When we look at b, it has to be something positive, so no negative bases, and b can't be 1. Now the reason we don't want b to be 1 is that when I put in a 1 from my base, I'm going to just be doing things, I'm just going to be doing 1 to certain powers. Well, 1 to any power is just going to be 1, so that's like the boringest function ever. It's just a bunch of 1s. And the reason we don't want to choose a negative base is because one of the things we saw with doing radicals and doing roots is that there are certain radicals and roots and different exponents for fractions that when I look at a negative base, it's undefined or comes out complex. So what we're doing essentially is to keep it real, we're going to make it so that our bases are always positive. So this causes the graph to have some very specific looks when it comes to what B does. So let me tell you a little bit about that. So when you look at the graphs of B, or sorry, graphs, that's grab. I was thinking about B. The graphs of f of x equals b to the x. It either looks of one of the two forms. Either it's going to be what we call a growth or a decay. So if b is between 1 and 0, that's the wrong way, 0 goes down there, and 1, then f is called a decay, and you'll see why when I do the graph. And when b is bigger than 1, we call f a growth. That's what you want to be. You want to grow as a people. Just to have us see what this looks like, let's do some graphs of examples of this really quick, so you can see why they're called a growth and decay. So I'm going to do f of x equals 3x, or sorry, 3 to the x. 3x we already did. That was linear stuff. We did that a while ago. And then I'm going to do g of x is 1/3 to the x power. And we'll see how this goes. So I'm going to graph this the old school way. I'm just going to do a little table and then plot some values, and we should be good to go. So let me just do a couple values here, and we'll figure out what the f is of them. So let's do like -2, -1, 0, 1, and 2, and that should give us an idea what it looks like. And I'll graph it right here, and then I'll do g as well. So x being -2 means that I have -2 in the exponent. Hopefully you remember that I can just move it in the denominator and square. And then, so this is 1/9. Similarly, when we look at -1, this will be 1/3. 3 to the 0 power will give us a 1. 3 to the first power will just give us a 3. And then 3 squared will give us a 9. So let's graph f really quickly. I think I'm going to graph them on the same axis so you can see how these two are related. So we'll call this 1, 2, 3, 5, oops, I want to mark 5, 6, 7, 8, 9, and then 10. I really didn't need to make this big. So I'm just graphing the first two. So f I'm going to do in red, and then I'll do g in blue to keep them separate. So, oh boy, at -2, it's -9th. That's going to be hard to graph. It's going to be close to the axis, real close. And then -1/3 is probably going to be like right here. And then at 0, it's 1. At 1, I'm 3. And at 2, you're 9. So I'm hoping you get a picture of what's happening here. As I head out towards the positives, this seems to be increasing very quickly. And as I play connect the dots, it curves and it heads towards 0, because as you picture what's going to happen here, your fraction is just going to keep getting smaller, but it's never actually going to reach 0. So it's going to get close to that axis, but never actually touch it. Let's do g in blue real quick. So we'll do x, and then we'll do g's. So we're going to play the same game. We'll do -2, -1, 0, 1, and then 2. We'll get our values, and we'll graph them together. And just in case you don't see the red color so easily, this is the f of x graph. Okay, so 1/3 to the -2. So remember, negatives we can interpret as just flip it. So this is going to be 1/1/3 squared. It's the same as 1/1/9, which dividing by a fraction you can invert and multiply. You'll get a 9. That was not easy. 1/3 to the -1. I can move it into the denominator to make it positive. And then 1 divided by 1/3, invert and multiply. I'll actually write this one because I can fit it. And that'll give me a 3. Everything to the 0 power is 1. That was easy. Everything to the first power is, well, it's just itself, 1/3. Woohoo! And then 1/3 squared will be, I just square the numerator, which gives me a 1. I'll square the denominator, which gives me a 9. So 1/9. Okay, so let's graph this at -2, -1, -2, I'm 9, so I'm up here. At -1, it's 3, so right there. And then at 1, at 0, it's 1. And then 1/3, which is roughly there. And then 1/9, which is even closer. And then let's do G. Do. This shouldn't have been angled off so much. I was trying not to hit the 10. That's G. So G is what we call a decay, because as I increase in x, the values go down and get really small. And then F is called a growth, because as I increase in x, it gets really, really big and grows really fast. So I'm hoping you picture what can possibly do this. And some things that definitely have exponential behavior are things like populations. They grow exponentially. Let's do some more graphing with this. So we're going to do some graph comparisons. So, example, for each FG pair, graph integers. Sorry, I had a hard time reading the word integers in my own notes for a second there. Between -2 and 2. And then describe how the graph F is related to G. So you're going to see their equations make them look like they have a relationship, and then hopefully you'll be able to pick up on the relationship as I graph them. So for my first pair, my f function is going to be 4 to the x, and my g function is going to be 4 to the x plus 1. So notice my plus 1 is in the exponent. So I'm going to graph these for my tables of values and describe how these two look compared to each other. So I'm going to have my x values first, which are -2, -1, 0, 1, and 2. And we're going to do f first. So as we've already seen, 4 to the -2, it's going to be the same as 1 over 4 squared, or 1/16. Super tiny. 4 to the -1, be 1 over 4, or 1/4. 4 to the 0, we already know what those zeros do. That's going to be a 1, although I started to write a 0 because that's the way my mind works. 4 to the first, that's just a 4. 4 squared, that's a 16. Okay, so I'm going to try to fit this. See if I can get up to 16. Oh no, no, I don't want that. Stop. Make my axis a little better this time. 1, 2, 3, 4. Do I really want to tick by 4? That's going to mess me up. Let's not do that. 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And if I go 1 above that, that'll give me 16. Got it. I made it fit. Beautimus. Let's get this F on here. I should have counted these by 4, and that would have made this much more convenient. Oh, too late. 2 is 16. 1 is 4, and 0 is 1. Oop, that's not 1, that's 2. Except for I decided it would be a good idea to draw them both anyway. There we go. And then I need 1/4, which is probably like here. And then 1/16 is going to be so tiny I can't even tell, but let's just draw it. Bam. There's the F. Where is your F at? It's right there. Cool. Let's do G. So G, just like I did before, I'm going to do in blue. And I'm just going to do it along on the same table to make it fit. So this is going to be my G. So x is -2. So 4 to the -2 plus 1. -2 plus 1 will give me -1. So this will be 1/4. 4 to the -1 plus 1 be 4 to the 0, which is 1. 4, and now I'm putting in 0 plus 1, which will be 4 to the first, or 4. 4 to the 1 plus 1 will be 4 to the 2, which will be 16. Then 4 to the 2 plus 1 will give me 4 to the third, which is Ooh, brain, come on. What's 4 times 16? It's 64. That is not going to fit on my graph. Oh well, let's graph G. Awkward. Okay, at 2 it's 1/4, so that's my 1/4 point from before, so I need that here. It's not at 2, it's at -2. And then at -1, it's 4, so 1, 2, 3, no wait, it's 1, so it's right there. And then at 0 it's 4, and then at 1 it's 16, and there we go. Play connect the dots because there's no way I'm fitting 32 on here. So what does it look like G's doing? G looks like it's exact same as F, but like switched over one. So I would say that G is F, shifted to the left by 1 unit. So what I'm noticing here is that, oh, that point that would have been there at 4 is now back here. That point would have been there at 0 is now back here. The point that would have been 1/4 is back here, and so on and so forth. So it's just back 1. And why is that happening? Well, because I added 1, all the stuff that would have happened in X here happens 1 unit sooner. So it's to the left, or back 1. Now using your power of perception of what happened here, I wonder how the next graph set is going to go. Let's find out. So let's take a look at what our next pairs are going to be first. So this is B. So let's say I want to do f of x equals 3x, and we want to compare that to g of x equals 3 to the x plus 2. But notice where the plus 2 is. It's not in the exponent. So it's going to be a different setup than the last one. So we're going to ask ourselves, what's going to happen if I add the 2 down here, not in the power? What's going to happen to the graph? Hopefully you have some instincts as to think what's going to happen. If not, that's okay. We're going to do it real quick, and then you'll see what happens. So I got my x's. I'm going to do -2, -1, 0, 1, and 2 to get an idea what f looks like. Let's do some f'ing. Let's do some f. Self-judgment. 3 to the -2. This is going to be the same as 1/3 squared, because remember you can make the exponent negative by moving it into the denominator. Hopefully you remember that 3 squared is 9. If not, you can calculate it real quick. 3 to the -1, so that's going to be 1/3. And then 3 to the 0, anything 0 power is 1. 3 to the first is just a 3. 3 squared will give us a 9. Oh, we did this one earlier. I should have just stole the graph from last time. Oh well. Let's make sure I make this straight and big. That is the best straight line I think I've ever drawn. I should give up. I'll never do one as good as that again. Just like, I need to quit. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's 10. Oh, and I made it too big. Oh well. See, shouldn't quit my day job. Made it too large. Darn it. Let's graph F. So at 0, it's 1. At 1, it's 3. At 2, it's 9. This one's kind of boring because I've done it once before. -1, it's about 1/3. -2, it's 9th, which is like so close you're not going to be able to see it on this scale. Curve it up. There's my F. Let's draw ourselves some G. Okay, so I'm going to have to do my exponent part and then add 2. So this is going to be 3 to the -2 plus 2. Now, luckily, I already have an idea of what 3 to the -2 is. It's 1/9 from what I just did. So it's 1/9 plus 2, or 2 and 1/9, which I could calculate, but I'm not going to because I think that's going to be easier to do on the graph. I'm going to go up 2 and then up a 9th, and that'll be a little bit easier. So I'm not combining those simply because it'll make it easier to graph here in a second. So that's just an elective choice. If you wanted to combine them as fractions because you've been totally insulted by my choosing to not add, I think this is 2, 9, 18, 1. It's 19/9. There you go. Which is, you totally can't graph that. Okay, so this is 1/3 plus 2. So to graph this one, I'm going to go up 2 and then a third. So this one, 3 to the 0 plus 2. 3 to 0 is going to be 1 plus 2 will give me a 3. So that one's going to be easy. And this one I did combine it because like it makes sense. Okay, 3 to the first plus 2 will give me a 3 plus 2, which is 5. See why I'm doing it for the lower ones, not the upper ones? I hope so. 3 squared plus 2 will give me 9 plus 2, which is 11. Let's graph this. So at 0 for x, it's a 3. So at 0, it's a 3. At 1, it's a 5. So 1, 1, 2, 3, 4, 5. And then at 2, it's 11. There's my g. Okay, now here's the hard part. At negative 1, it's 2 and a third. So at negative 1, I got to go up 2 and then about a third. And then at negative 2 for x, the result in y is 2 and 1/9. So I got to go up 2 and then a 9th. That's hard. Hopefully you're picturing what's happening here, what actually happened. Plus or minus my ability to draw straight. What's it look like g is? It looks like I just took f and went up 2, doesn't it? Look at where the points went. Oh yeah, and that's exactly what's happening here. Oh, I didn't mean to pull up my keyboard. Sorry, I hit the wrong button. So what's happening? G is f shifted up 2 units. So I'm hoping what you see is if I add outside the exponent, it moves you vertically. And if I add inside the exponent, it moves you horizontally. Let's make note of that real quick. That was supposed to be a H and it came out looking horrible. I'm using the word moves, but really what I mean is shifts the graph, which means moving the graph, so I don't know why I'm saying this differently. Vertically. I love how vertically has the word tickly in the middle of it. It makes me giggle. Fun. Let's take a look at the natural base E, because, well, we're going to, and that's the last topic of this section. Good times. So we talked about this previously, how E is like just this number that's irrational because it can't be written as a fraction, that has this unending decimal that has a pattern, but it's not a pattern that allows you to place it into a fraction, like pi. It's a number. It's irrational. It can't make up its mind to stop as a decimal. That was a bad joke. Anyway, if you want to know what it's doing, E in reality can be defined to be 1 plus 1 over n. So I'm taking 1, adding a fraction to it to the nth power, and then letting n approach infinity. This will become relevant later. So what's happening here is I'm taking E and I'm saying, hey, well, I'm taking a fraction, I'm letting it get smaller and smaller and smaller and smaller because I'm letting this value down here in the denominator get teenier and teenier and teenier. But the exponent's getting bigger and bigger and bigger, bigger, bigger. And as it turns out, when you do that, as it goes out towards infinity, it approaches a single number. So that's where E came from. So you might ask yourself, where did this come from? And the answer is, it comes from compound interest. So let me talk to you about what compound interest is. So compound interest is what happens when you save money or have to make payments. So you'll have some amount you initially put into an account, P, called the principal. So usually we'll call this the principal investment. And then you'll have R, the amount of whatever the rate of the account is. So maybe you got 4%. So this is your rate of interest. And then N is the time periods for compounding. So this is where things get a little bit complicated. I'm going to say this a little bit differently. We're going to call N the number of compounds in a year. So if you have a bank account that is a savings account, they'll usually earn interest monthly. So if it was monthly, then it will compound 12 times in a year, once each month, and there are 12 months in the year. That's probably the most common. So that's what N is doing. And then T will be the amount of time that you let the account run. So maybe you're going to let it go for like 5 years or something like that, and then you're going to pull all your money out and buy a house or something. So this is just going to be time. And we're going to usually do this in years because, well, that's what N is. And then A is going to be the amount in the account. At time T. So pulling these all together, you get the compound interest formula, which is A, I take my principal and then I add to it my interest, so it earns interest. How often does it earn interest? Well, it earns it N times a year for T years. So that's where all the parts come together. So be careful when you're looking at this. There's a lot of moving parts, but it should look like an exponential function, and this is a function of t. T will be the things you usually change. Let's do a couple compound interest examples so you can see how all these parts work together. So for this example, I'm going to use the same amount of money, but then compound it a bunch of different times. So we're going to find the amount, which is going to be A, in an account. Hold on. Accumulated over 5 years with an initial investment of $7,000 at a rate of 4%, and then dot dot dot, because I'm going to do a bunch of different compounds. Here we go. So for the first one, I am going to compound it monthly. So for this first example, every month you would earn a little bit of interest. But over the year, you would earn 4%. And we'll see how these amounts differ when we start doing the equations. So to do this, I'm going to take my $7,000. I'm going to have my interest rate. For our interest rate, we're going to always convert it to a decimal, so I'm going to use 0.04. And then, since it's monthly, my number of compounds is 12. And then 5 years, so this will be 12 times 5. So what I would do if I were you is instead of doing 12 times 5, you would actually calculate what 12 times 5 is ahead of time, which in this case it's 60. And I would do that first, because having two things going on in that exponent we've already seen makes the Microsoft calculator be angry. So we want to avoid that frustration of having something get wrong. Now be careful, I am going to round this, but I'm going to round it to 2 decimal places because it's money, and hopefully that makes sense to you. So pull out your calculator and you should calculate this. So common mistakes people will make with this is when they're doing the 1 plus 0.04 divided by 12, they'll round that and then multiply by 7,000. Don't do that. Remember, the exponent comes first in the order of operations. When you do this, you should get $8,546 and 98 cents. Now I'm rounding it up to 98. You should get 97.6 and then some change. So be careful. So that's what it would look like if you earned interest every month. Let's look at a slightly different scenario. So we're going to compound instead of every month, compounded semi-annually. So for those of you who don't know, semi-annually means twice a year. Biannually means every 2 years. These are two that are commonly confused. Very commonly confused. I know I mess them up every once in a while. Then I remind myself, oh, they're having a semi-annual sale. Oh, those happen twice a year. Yes, shopping has saved my math life. Maybe it'll save yours. Okay, everything's the same except for my n value. So here's where you have to be careful. So I'm only going to divide by 2 here, not 12, because it's only happened twice a year. And then it's going to be 2 times 5, or 10. So notice my exponent changes, and so does part of my base with the interest rate. So I'm hoping you look at this and you're like, oh, well, I wonder what's going to happen. Is this going to be less money or more money? Hopefully your mathematical instincts are that it's going to be less money because I'm going to get less compoundings. I'm going to earn interest less times. So it makes sense that I should earn less money. And when you calculate this, it is less money, but not by much. You're only off by just a little bit. Yeah. So $8,532.96. So you lost like 14 bucks, which isn't much. But if this was a much larger investment, like, I don't know, $700,000, you'd be like, heck yes, give me my, like extra 6,000 bucks. You don't want to lose that monies. Nobody wants to lose money. That's been my general life experience. Anyway, next up, we're going to do what's called compound continuously. Now, I haven't done one of these yet, but they are different. So compound continuously means n approaches infinity. So I'm going to be using e for this. Why can't I write infinity? So instead of using my amount equals my base, why did that move? No, stop it. Instead of having my base be this 1.04, I'm going to be using a different equation. I'm going to be using what's called the PERT equation. Why did I start with P? P goes here. E to the RT, where R is my rate, T is my time, and P is my principal. So for this example, I'm going to have 7,000 E to the 0.04, and then my time is 5 years. And as you'll see, this comes out close to the ones we've had previously, but it is different in value. So pull out your handy dandy handheld calculator, go ahead and put in your values, and you should get the same thing I do. Now, same tip as before, if you're having difficulty, multiply the exponent first and then go ahead and do the calculation so that you get the correct values. And when you do, you should get $8,549.82. So what does this mean? If I did an infinite number of compounds, the biggest my money could be would be $8,592.82. That is the largest it could possibly be. So when we compare these, they're all pretty close, but compounding an infinite number of times obviously is going to give us the largest number of values. So if you want to compound every minute of every second of every partial second of every 1/10 of a millionth of a second every day, compound continuously represents that. So if you want to also think about this, this is the most your investment could come out as, because it's the most interest it could possibly earn from a 4% account. So in looking at this, this is a good way to measure, is it a good investment? Hope you've enjoyed this application of the exponential, and that's all I have for you today.